Hi, in this video, we are going to look at an interesting application of the concepts that we have learned so far. So this is powers modulo m. So for example, if you had a question like this, how do you find 5 to the power, let's say 10 power 14 modulo 12830,603? Now this is a really difficult question. Like you can't do it with a calculator, right? Because you can't input 5 to the power 10 power 14 and the modulo is also pretty large, right? So we want to find a strategy by which we can evaluate it with minimal calculations. Obviously, we'll have to do some calculations, but it is much easier than actually trying to find this because this will have the number of digits here will itself be super large. So you can't really evaluate it directly using a computer. You need a better method, right? So what tools do we have here? We have Fermat's theorem. Fermat's theorem says that if you have a prime number p and a number a which has GCD of 1 with p, we have a power p minus 1 is congruent to 1 mod p, right? Uh, so if you have a prime number in the modulo, then we can possibly use Fermat's theorem. But then you'll have to check whether this is a prime or not. 12830,603, right? A little bit of checking will tell you that it is actually not a prime and it's actually composite and it is equal to 3571 times 3593. These are themselves prime numbers. So you should first question how would you find these prime factors. So that is a little difficult, but checking whether something is a prime or not is pretty easy by the method that we will see in today's class. So I will tell you a method by which we will learn how to find whether a number is a prime or not in a fairly simple manner. Okay. So for now, you will just have to accept this, that you can check it out by multiplication. This is a composite number. So if the modulo is composite, we can't apply Fermat's theorem, right? So let's look at Euler's theorem then. Euler's theorem says that we have a power phi of m is congruent to 1 mod m. Here m doesn't have to be a prime, right? So modulo m, so this was our m, so we should basically find phi of 12830,603. And since Euler's totient function is multiplicative and its prime factorization is this is equal to phi of 3571 times phi of 3593. And since both of them are prime, the phi of them will be p minus 1. So this is 3570 times 3592, which comes out to be basically another big number, but it is smaller than what we started off with, 128,23440. You can check this with a calculator. So phi of this is equal to 128,23440, right? Now, since we know that we know the phi, so basically I can figure out a power phi of m and that should be 1 mod m, right? So we have power here is 10 power 14, right? So if we do division algorithm, we can say 10 power 14 is equal to something quotient times phi of m plus some remainder, right? Where the remainder will be less than phi of m. Now, if you think about it, my phi of m is this. So I will divide 10 power 14 by 128,23440, and you can calculate that. This comes out to be 7798219 multiplied by 12833 1282340 plus there is a remainder, and the remainder is 6546640. So what I have done is applied division algorithm to the numbers 10 power 14, which was the power here, and my phi of m. What is the benefit of that? Now I can write 10 power 14 as this, right? So basically, I will show you in the next page. You have 5 power 10 power 14. That can be written as 5 power 128 23440 multiplied by 7798219 multiplied by 5 power 6546640. Basically, this is 128 23440 multiplied by this plus this, which is same as 10 power 14. That's why we did division algorithm. Why is this useful? Because Fermat's theorem guarantees that a power phi of m is congruent to 1 mod m. And here a power phi of m was what? 128 23440 should be congruent to 1 mod of the m that we started out with, which was 128 30603, right? So we know a power this is congruent to 1. So this part becomes congruent to 1. So we have congruent to 654664440, right? So 5 power 10 power 14 is congruent to this mod of m, which was 128 30603. So we have reduced our problem to a much smaller problem. You should realize that 10 power 14 is so much bigger than 6546640, right? This is like 6.5 million, and this is like 10 power 5 billion, right? The power here is 10 power 5 billion, and this is 6.5 million. So at least we have reduced the problem significantly by using Euler's theorem, right? So once we have reduced the problem, our job is now basically finding the modulo of 6546640 5 power 6546640 modulo 128 30603, right? This is our problem now. Now, how do we do this? This is the subject of this video. The method to calculate this is what we are going to learn. And what we are going to learn is called the method of successive squaring. Successive squaring method. It has a lot of applications. Like you can build a computer program which does the successive squaring for you. It's a simple algorithm which you can easily code, and you'll be able to get the powers, very high powers. You'll be able to figure out modulo m, right? So let's try to understand the method with an example. So my job is try to find 7 power 327 mod 853. Okay. This is what we want to find out. Now, how do we do it? The first step is to create a table modulo 853 of all the powers of 7 in a successive squaring method. So I will just show you the table. So 7 power 1 is congruent to obviously 7 mod 853. 7 square, I will square this. 7 square will be congruent to 49 mod 853. 7, now square this. So 7 power 4 is congruent to what? It will obviously be 49 power square, 49 square, which comes out to be congruent to 2401, which is congruent to 2401 is congruent to 695 mod 853. So you find the squares and then you take mod 853 to get your final answer. Similarly, 7 power 8 will be congruent to, basically you have to do 695 square now. Technically, you have to do 7 power 8 calculation, but we already know this. 7 power 4 was this, so 695 square, and that will come out to be, after calculation and after taking mod 853, it comes out to be 227 mod 853. So I hope you are understanding how we are building the table. We take 7 power 1, then 7 square, 7 power 4, and we calculate mod 853 for all of them, right? And notice that each number here, you have to square this number and take modulo 853 to get the next entry in the table. So here we did 49 square and then take modulo 853 for that to get 695. So like this, we can build up the table. I will just give you the values for 7 power 16. That comes out to be 349 mod 853. 7 power 32 comes out to be basically 675 mod 853. 7 power 64 comes out to be 123 mod 853. And similarly, we can find 7 power 128 also and 7 power 256 also. I'll just write it here. 7 power 128 comes out to be 628 mod 853. And 7 power 256 comes out to be 298 mod of 853. We are going to build our table of successive squares till we get the highest power less than 327, right? We don't want to do 7 power 512. We don't need it. We only need it till 256 because we need to find out 7 power 327. So this is the first step. The first step is basically construct a table of powers mod m by successive squaring. So we have constructed our table. We have our values of the powers of 7 mod m, right? Now what is the second step? Second step is look at the power that we have. We have to write 327 as the sum of powers of 2, as the sum of powers of 2. Okay. So what is this? 327 can be written as 256 plus 64. 256 plus 64 becomes 320 plus 4, see 324 plus 2 plus 1, right? So this is the power written as the sum of powers of 2, right? Now think about it. In the third step, we just try to calculate 7 power 327. So this is equal to 7 power 256 times 7 power 64 times 7 power 4 times 7 power 2 times 7 power 1. And if you take modulo 853 from our table earlier, we know the values of 7 power 256, 7 power 64, all of them we know modulo 853. So I'll just use that table to write 123, then 695, then 49, and then 7 mod 853, right? We have these values. Now, how do you calculate this? You can find the overall multiplication and then take mod, or you can do step by step. You can multiply these two and take mod 853. So that will become basically 828 times 695 times 49 times 7. And then you can multiply these two and take mod 853. That becomes 538 times 49 times 7. In the next step, take these two, multiply these two, take mod 853. It becomes 772 times 7. And finally, multiply these two and take mod 253. It becomes 286 mod 853. So in a step-by-step manner, we can calculate this. And basically, we have found 7 power 327 is congruent to 286 mod 853. So this is your successive square method. The algorithm is pretty simple. So what are the steps involved? I will just list them out once more. First of all, let's say we have to calculate a power k mod m, right? The first step is to write k as the sum of powers of 2. So k can be written as u0 plus u1 times 2 plus u2 times 2 square and so on till ur times 2 power r, right? That is my k. Second step, write a table of powers of a mod m. So basically we want a table like this. A power 1 mod m is congruent to, let's say, A0 mod m. Similarly, A square mod m is congruent to A naught square is congruent to A1 mod m. Every next entry in the table comes by squaring the output of the first entry, A naught square, and take mod m, that is A1. Similarly, A power 4 is going to be A1 square, which is congruent to, let's say, A2 mod m, and so on. So once you have built your table of powers, what we will do is we have to find out A power k. A power k will be A power u0 plus u1 into 2 plus u2 into 2 square plus ur into 2 power r. So that will be A power u0 multiplied by A power 2 times u1 multiplied by A power 2 square times u2 and so on, A power 2 power r times ur, right? Now A square, and we have to calculate all of this mod m. So think about it, A square was equal to A1 mod m. So this is capital A1 and this is A power 1. So this is A power 1 power u0. So A power 1 was A0 power u0. So you have to do A0 power u0 and here you have to do A1 power u1 and here you have to do A2 power u2 and so on. And finally take mod m, right? So the method is pretty simple. Write the power k in terms of powers of 2. Try to find the successive squares of A mod m and then use those results after splitting A power k in this fashion, right? We have already seen an example where it worked, so you should apply that. Now, one very interesting application of this is basically using successive squares method and Fermat's theorem, we can find whether a number is composite, whether a number m is composite without factoring it at all, without factorizing it. So that is interesting because if we have a big number, it will be difficult to prove that it is composite or prime. If you have to actually write down all the factors, it will be annoying to do. So let's say we have a number a, right? Not a, let's pick a number m. Pick a number m. We have to figure out whether m is composite or not, right? Now the steps involved are this. Take any number a less than m, calculate the GCD of a and m. This GCD can be calculated by Euler's Euclid's method, the division algorithm, right? Calculate the GCD. If GCD of a and m is greater than 1, then they have a common factor, obviously. They have a common factor bigger than m, which implies that m is composite. If the GCD is greater than 1, that means there is a common factor of a and m bigger than 1, which means m is obviously composite. It is divisible by that factor. If GCD of a and m is equal to 1, then we go to the next step, right? We can find a power m minus 1 mod m. If the GCD of a and m was 1 and they were relatively prime, you try to find a power m minus 1 mod m by the method of successive squares. By successive squares method, the one that we have just now learned, right? Now, the point is, if m is prime, the answer by this method, answer should be 1. If m was prime, this is a power p minus 1 mod p. So the answer should be 1. If the answer is not equal to 1, if the answer is not equal to 1, that means m is composite, right? So the idea is you are checking whether the number and m satisfies Fermat's theorem or not. So if a power m minus 1 mod m is coming out to be not equal to 1, obviously m cannot be prime, right? Notice one thing here. If you calculate this mod m, if the answer is not equal to 1, m must be composite. That is correct. However, if the answer is equal to 1, it is not guaranteed that m is a prime. It is highly likely that it is a prime, but it is not guaranteed that it is a prime, because then you will have to check whether a power m minus 1 mod m is also equal to 1 for some other value of a, for some other value of a, and you'll have to check it for different values of a. If it comes out to be 1 for all the values of a, then it is a prime. So it's not guaranteed that m is a prime here if it is equal to 1. If it is not equal to 1, there is a guarantee that it must be composite, right? This is a consequence of Fermat's theorem. For example, I'll give you an example. There are composite numbers. M such that a power m minus 1 is congruent to 1 mod m for all a such that a and m have GCD 1. So basically for all a's co-prime with m, there are composite numbers m such that a power m minus 1 is congruent to 1 mod m. So it satisfies this condition, and it actually turns out to be a composite number. Such numbers are known as Carmichael numbers. Carmichael numbers are composite numbers that satisfy Euler's Fermat's theorem. Basically, Fermat's theorem was true for prime numbers, but sometimes some special composite numbers are there which satisfy Fermat's theorem as well. Okay, so Carmichael numbers are those, and the first Carmichael number is 561. You should check 561. So basically, you can pick any a which is co-prime with 561, and you will be able to prove that a power m minus 1 is always congruent to 1 mod m, right? So try it out. You will realize that there are properties of Carmichael numbers which are quite nice. However, the point was we should be able to test whether a number is composite or not. This test always works. If a power m minus 1 mod m comes out to be not equal to 1 for a co-prime with m, then that number m must be composite. So we have learned how to do that test by the successive squares method. Now, you should try out a few powers. Just take arbitrary powers. So for example, I will leave these as an exercise for you. Calculate 5 power 13 mod 23 by the successive squares method. Also calculate 28 power 749 mod 1147. Also calculated by the successive squares method. You will realize that it's a very powerful tool. You should not be able to do this very easily if you don't use this method. So try it out. Hopefully you will see the benefit of this. Also, what we will find is we will come back to Carmichael numbers and come back to primality testing in a future video. So for now, that's it. I just wanted to show you the powers modulo m, how to calculate it using the successive powers method, successive squares. So that's it for this video. I'll see you next time.